Hello, everyone. Welcome back to our seminar. Today, Jane Breen is going to tell us about Kemeny's constant for Markov chains and random walks on grass.
Thanks very much, Maria, and thanks for inviting me to give a talk in this session. I'm going to give my excuses up front just to save myself. So I realized this time 2 weeks ago that my colleague and wonderful collaborator, Sooyeong, was talking on the same topic. And so I emailed and I said, I was kind of going to talk about the same thing. Do you want me to change it up a little bit? So I've tried to kind of change the content so that it complements Sooyeong's talk. If you didn't see Sooyeong's talk, you should go and watch it in the recording because it's a great one. But I'm going to kind of try and talk more about some generalizations of random walks on graphs, just a little bit to keep it a bit different. And so hold on now, this is so the overview, like the high level, just here's what you need to know in advance, is that Kemeny's constant is a measure of how well connected the states of a Markov chain are. And there's an explosion of work studying Kemeny's constant for a graph as like a spectral invariant for a graph. And this comes from thinking about the random walk on the graph as a Markov chain. And so you look at Kemeny's constant for that. Now you've got a nice measure of how well connected the vertices of a graph are. And so the thing I'm going to kind of talk about a little bit is what kinds of generalizations can we make of Kemeny's constant for a graph. Now, obviously, like a Markov chain is the most general scenario where you can talk about Kemeny's constant. But what I kind of want to do is like I'll talk about Kemeny's constant in the context of Markov chains and then like narrow in on the random walks on simple undirected graphs thing, and then just like take one step out from there to kind of generalize from there, right? So that we're still staying within the algebraic graph theory setting, hopefully. Okay, so, but like I said, like I think it's important for to talk about, hold on, this doesn't seem to be playing ball. Okay. I'd like to talk about Kemeny's constant from the ground up, like introducing Markov chains to start with, because I think it's important to remember like the interpretation of Kemeny's constant as it comes from there, rather than just evolving into this is a nice new spectral graph invariant. So if you know all about Markov chains already, you can tune out a little bit and I'll call you back in when it's time. But for us here, a Markov chain, we're going to think about finite, discrete time homogeneous ones, which you can just think of a system that at any given time occupies one of a finite number of states, and then transitions from state to state in like discrete time steps. And then for every state you've got, for every pair of states you have, there's some probability that you transition from one state to another in a single time step. Okay, so these are called the transition probabilities. And then the way I've set this up, it should be clear that once you occupy one of the states and you know the transition probabilities to all the others, that what happens next depends only on the current state of the system. So if I know I'm in state 2 and I've got all of these transition probabilities of where I go to next, then this tells me what happens next. So it doesn't depend on any previous history, just on what state I'm currently in. That will be important later because we're going to expand that a little bit. So you take your transition probabilities, you arrange them into a matrix, and now you've got a row stochastic matrix that describes everything that you need to know about your Markov chain. So here, your second row of this matrix, the corresponding entries tell you the transition probabilities to the other states. So the 2-1 entry is the probability of going from state 2 to state 1 in a single time step. Okay, so everything you need to know, you can calculate using the transition matrix T. So if you want to know the long-term behavior, you can take powers of this matrix T. And in the nice circumstances that we're going to think about, where you've got an ergodic Markov chain, every row of your transition matrix converges to the same thing. And that same thing is a left eigenvector of your transition matrix, corresponding to the spectral radius, the eigenvalue 1. Okay, so you just normalize that a left eigenvector, and you've got a probability vector that represents the stationary vector of the Markov chain. And so the ith entry here gives you like the long run probability that you occupy the ith state. Okay, so for this example here, here's my stationary vector, and you can see that it's far more likely in the long run that I'm in the 4th state. And if you kind of stare at the transition matrix, this becomes intuitive, right? Because if you're in the 4th state, then with probability 3/4, you stay in the 4th state. So you end up kind of spending a lot of time there. Even if you step out to go back to state 3, there's a high probability that from state 3, you go to state 4 again. And so that's why we're seeing here that this is a much higher value in my stationary vector. So I spend more time. This is a more important state in my Markov chain. Okay, that's long-term behavior. For short-term behavior, I'm not going to go into the details on how you compute anything to do with this, but the mean first passage time is kind of how we encompass the short-term behavior. This is the expected number of time steps it takes you to reach state J, given that you start in state I. And so you call this MIJ. This is the mean first passage time from I to J. And you also calculate this using the stationary vector. So sorry, not the stationary vector, the transition matrix. So here's the expression. You don't need to know it. You just need to know that you can calculate it from the transition matrix. Okay. So again, going back to our example, for the mean first passage times from state 1 to state 2, the expected time it takes you to get to state 2 from state 1 is just one step, because if you're in state 1, then with probability 1, you go there in the next step. But the expected time it takes you to go from state 2 to state 1 here, if you calculate it, is actually 20 times step, because once you're in state 2, if you're moving randomly according to these transition probabilities, you spend a bunch of time. The expected time it takes you to return to state 1 is 20 steps, because you can spend a lot of time in states 3 and 4. Okay. So if you need an example to keep in mind, other than this kind of constructed example that I've got, you can think about random walks on graphs, which is what we're going to think about most of the time, where now the states of your Markov chain are vertices of a graph. And then if you are in one of your states, then you choose one of your neighbors to move to with equal probability. So if I'm in state 2, then I have 3 neighbors to choose from, and I choose each of them with probability 1/3. So this gives you your transition matrix, which is just the adjacency matrix where you've normalized the rows according to the degrees of your vertices. Okay, and I'll mention as well that the stationary vector here, the entries are proportional to the degree, which means that the importance of a state in this Markov chain is the higher degree, the higher degree vertices are more important. You spend more time on those in the long run. Okay, have we any questions before we keep going? I don't know how to find the chat. Here we go. I'll put this over here. All right, if not, we'll keep going. So the reason I introduced both of these things, W and M, the stationary vector and the mean first passage times, is because they're both involved in our expression for Kemeny's constant. Okay, so Kemeny's constant, let's say we've got a transition matrix that corresponds to an ergodic Markov chain. It's got n states, and we've got its stationary vector, and we've got its mean first passage times. So we're going to fix a starting state I, and we're going to define this quantity here, where we take the sum over all j that's not equal to I, and then it's Wj times Mij. So this, you can think of this as the like a weighted average of the mean first passage times from your starting state that you fixed to like a choice of all the other ones, where you weight them according to the stationary probability. So you can interpret this quantity as the expected time it takes you to reach a randomly chosen state J, starting from state I. And so the kind of crazy thing about this is that this is a constant, and it doesn't depend on what you choose for I. You get the same value regardless. Okay, so this is Kemeny's constant. This is where the name comes from. And so you just drop the index, just call it Kemeny's constant and associate it with the transition matrix T. You get the same value no matter which index I you choose. And it turns out that like it's not too hard to take that expression and manipulate it and show that you've got Kemeny's constant is also equal to this double sum, where it's like a weighted average of all the mean first passage times between starting and ending states, where both the start and the end are chosen at random with respect to the stationary distribution. Okay, so now you can get an interpretation of this as the expected length of a random trip in the Markov chain. And so the lower this value it is, the easier it is to get around the states of your Markov chain, and the higher it is, kind of the harder it is to get around. Okay. All right, so I can't talk about Kemeny's constant without very briefly talking about the history of it, because I think it's kind of fun. And so let's see. Sorry, I can't see with this thingy in the way. This goes over here too. Okay. So the first mention of Kemeny's constant comes from the textbook by Kemeny and Snell on finite Markov chains from 1960. And so this book, a lot of the content in here revolves around this guy called the fundamental matrix, where you take your transition matrix and it's like a generalized inverse of I minus T here. So it's this matrix Z, you form this rank 1 kind of addition to I minus T and take its inverse. And lots of things you can calculate using the fundamental matrix. So for example, there's an expression for the matrix of mean first passage times that's just dependent on this matrix Z that's calculated. Okay. So a lot of the book is a bunch of different theorems about the things you can tell about the evolution of the Markov chain and different things using this fundamental matrix Z. And so somewhere along the way, at the end of one of the chapters, there's this theorem where they say, okay, well, let's look at the trace of this matrix Z. So C now is the sum of Zii. Then if you take M, which here is their matrix of mean first passage times, and then alpha transpose is the stationary vector, but written as a column vector, then you get C times, and then this Greek letter here represents their all ones vector. Okay, so translated, if you look at the statement of this theorem, what this is saying is that M times W is this constant times the all ones vector. All right, so this is, you know, just your sum over J of Mij times Wj. And the proof is 3 lines long. And all it is like a matrix computation, right? M, you just substitute in that expression I showed you on the previous page involving the stationary, the fundamental matrix. And you just like, it's okay, I'm sorry, there's 4 lines because there's an extra thing missing here, an extra line hiding here. But that's it. And then the chapter ends and then we move on. Nobody talks about like how it's interpreted, how it's weird that you get the same value no matter what you choose for your index I. That's just all there is. And clearly there was some conversation about it between 1960 and 1975, because in a subsequent book by Snell in 1975, on the last page, there's an exercise where it says, okay, if you take the trace of this matrix, and here they subtract 1 to account for mean return times, which we won't talk about too much, but it's the same concept, same idea. This is equal to K, no matter what you choose for I. The constant K is called Kemeny's constant, and a prize is offered for the first person to give an intuitively plausible reason for the above sum to be independent of R, right? Where R here is your starting state. Okay, so this I think is like what makes Kemeny's constant so interesting. There's like this kind of weird lack of intuition around it. And we see this in a lot of results that are proven as well, that a lot of the kind of things that we prove, you're kind of like, huh, this kind of like doesn't really behave quite the way I'd expect. So it's kind of fun in that way. There was a bunch of stuff, you know, suggestions as to why it's constant. In the second edition of this, there's like, you know, a second exercise where Peter Doyle has suggested a certain interpretation, you know. Do you think he should have been given the prize? He was given the prize, but we won't get into it any further here and for the sake of time. And so kind of moving on from there, I think the next main result, as far as I'm concerned, was this short paper in the American Mathematical Monthly written by Levine and Loiseau in 2002, where they talked about Kemeny's constant and interpreted it in the context of a random surfer on the World Wide Web, which at the time would have been very trendy and of course got a lot of attention to it. And the main contribution here is that they had an expression for Kemeny's constant that wrote it in terms of the eigenvalues of your transition matrix. So like it was the trace of this generalized inverse. And so it's not too much of a leap to get an expression like this, but this is the first place that I think it appeared. And so from there, it now became, everybody loves eigenvalues, right? So then from there, it became something that, right, we can look at this, this will be good. So to give you an example of the kinds of things you can now do once you've got an expression in terms of eigenvalues, well, you can prove all kinds of bounds on it. So for example, if you've got any Markov chain, an ergodic Markov chain with a transition matrix T, the absolute smallest that Kemeny's constant can be is n minus 1/2, where you've got n states in your Markov chain. And I'm going to give you the proof of this just to scare you a little bit as to what things look like in the Markov chain world when you don't get to deal with a graph. It's not that scary. It's actually very straightforward. The proof goes like this. All right, so if you have your eigenvalues of your transition matrix, then the modulus of each one is less than or equal to 1. And so if you substitute one of these eigenvalues into that 1 over 1 minus lambda thing, then you get, it's greater than or equal to 1/2. I think we're all on board with that. Oh, but your eigenvalues could be complex, which you never have to worry about if you're only thinking about symmetric matrices, right? And so if you have a complex eigenvalue, it's fine, because complex eigenvalues have to come in conjugate pairs. So you just add those two terms together in their pairs, and like a good high school student, you find a common denominator and you simplify and you sub in your a plus bi and your a minus bi, and then, well, a squared plus b squared is the modulus of your eigenvalue. It has to be less than or equal to 1, and so overall the denominator is smaller than the numerator, and so this has to be greater than or equal to 1. So whichever way you slice it, like whether you take your terms here on their own when they're real, or if you take two of them together when they're complex conjugates, overall you can't exceed n minus 1 over 2. You've got n minus 1 terms here, and either on their own or in pairs, they're not going to amount to more than n minus 1 over 2 when you add them all up. Okay, and you might wonder, well, what kinds of transition matrices would have the absolute smallest Kemeny's constant? So it's as easy as possible to get around the states of my Markov chain. And the extremal example here is just the random walk on a directed cycle, where when you're at any state in your Markov chain, you have no choice except to move on to the next state and go all the way around. Now, this is kind of weird because this is essentially not stochastic at all, right? So at every state, then you've got one choice to go to and you move on from there. So this minimizes the expected time it takes you to get around. Like, sure, there's places where it takes you a long time, but on average, where everything is here equally important in your chain, this is the guy that minimizes Kemeny's constant. Hi, Maria. Yeah, what's up?
The minimizes Kemeny's constant in the cycle. Is cycle the only example?
Yes.
Yes.
Yes, this is the extremal example. Yeah.
Mm-hmm.
Are there any other questions?
Thank you.
Okay. All right. So let's quickly talk about I don't want to dwell too much on this because Sooyeong did a great job 2 weeks ago, but I'll talk a little bit about Kemeny's constant for random walks on graphs. And so, of course, if you've got a random walk on a graph, we've seen that the transition matrix, you just take the adjacency matrix and normalize the rows. So you can just find the eigenvalues of that matrix. And then that's your expression for Kemeny's constant. All right. Now, if you would prefer, like, it's not hard to show that the eigenvalues of these are real, it's diagonally similar to a symmetric matrix. But if you would prefer, entrench yourself in something that's symmetric and so on, then you can work with the normalized Laplacian matrix. So this is the definition of it. I think we have to assume that there's no isolated vertices for this definition to work. But here you've got the d minus a Laplacian in the middle, and then you normalize by d to the negative 1/2 on either side. And so it's not hard to show that the normalized Laplacian is similar to the identity matrix minus your transition matrix for the random walk on a graph. And so it's easy to show that the eigenvalue expression that you get here involving lambda j's is just this expression in terms of the eigenvalues of the normalized Laplacian as well. Okay. And so there's so I've said eigenvalues and related expressions. So you can also express Kemeny's constant in terms of things involving the characteristic polynomial. So if this is the characteristic polynomial of your normalized Laplacian, then Kemeny's constant is a minus C2 over C1, where C2 is your coefficient of the x squared and C1 is the coefficient of the x. And this comes from the fact that you've got symmetric functions of your eigenvalues as the coefficients here. And this is where you get this. Okay, so once you've got these kinds of tools in your toolbox, then you can prove things like, so the minimum value for Kemeny's constant for a random walk on a graph now is not quite as low as it is for that directed cycle. And it's also achieved by a much more stochastic looking thing, right? So Kemeny's constant for the complete graph, it shouldn't surprise you that this is the easiest graph to get around, right? So the minimum value for Kemeny's constant, and it's n minus 2 plus 1 over n. And then the maximum value for Kemeny's constant is conjectured to be achieved for this kind of barbell graph, where you take a third of your vertices and put them in a clique on one end, third of them in a clique on the other end, and you join them by a path of length n/3 as well. And so this one is kind of like, this barbell graph is a classic extremal example for a lot of random walks quantities. So the relaxation time, which is 1 over that first eigenvalue, right? So the spectral gap of your normalized Laplacian. This was shown by Aksoy, Chung, Tate, and Tobin in 2018. So the barbell graph was shown to be the extremal graph for this guy, and the value of 1 over mu1 is on the order of n cubed here. And then, while it's not proven to be the extremal graph in this paper by myself and Steve Butler and Kate Lorenzen and a lovely group of, oops, sorry, I've gone backwards, have I? Yep. A lovely group of undergrads, we calculated Kemeny's constant for this guy using these characteristic polynomial techniques, and then some other nice theorems involving twin vertices and twin subgraphs, and being able to make use of symmetry in the graph to kind of make the computation easier. And so this is conjectured by Aldous and Phil to be the extremal graph for both. And yeah, so these are the kinds of things you can think about with these eigenvalue expressions in your pocket. All right, now Sooyeong's talk the last time talked a lot about this other method of computation involving spanning two forests, where you have to count the number of spanning forests in your graph that consist of two trees, where one tree contains vertex I and the other tree contains vertex J. And when you count all of those for every choice of I and J, you get an expression for Kemeny's constant that involves like a kind of enumerative approach to calculating Kemeny's constant, where here you're weighted by the degrees of your vertices as well. So it's related to like you can see where the original expression is coming in. And we've just dealt with the mean first passage and by calculating the number of spanning forests. And so with expressions like this, in the context of simple random walks on simple undirected graphs, this is particularly useful when you're thinking about graphs that have cut vertices or bridges, right? Because now when you're counting spanning trees or spanning forests, you can kind of reduce it into the two pieces of your graph that are created when you remove your cut vertex or remove your bridge. So there's a couple of papers there I can refer you to, and Sooyeong had a great talk at the last day where he talked about Nordhaus-Gattam type problems that where these trees, the spanning forests, were used to calculate bounds on Kemeny's constant for a graph and Kemeny's constant for the complement of the graph. Okay. And so there's all kinds of graph classes that are studied for Kemeny's constant, but I would also mention that like a lot of them kind of are very specific families, because it turns out that working with Kemeny's constant can be quite tricky. Like both of these expressions, or all of these expressions we've seen, are a little bit annoying to work with, even when you know quite a lot about the eigenvalues of the graph in the first place. So there's a bunch of graph classes that have been studied that you can look into. If you're interested, send me a message. But what I want to talk about is like, well, let's move a little bit away from simple undirected unweighted graphs and see what kinds of interesting questions you can ask about Kemeny's constant if you're going to just take one step in a direction away from that class of problems, right? Because there we're comfortable and we can use a bunch of stuff about eigenvalues of graphs that we know from other contexts and just kind of pile them into formulas. It turns out to still be very hard. So there's no shortage of good questions in the simple undirected case. But let's do something a little bit different just for fun. And so the two extensions I'll talk about are random walks on weighted graphs. And now for me, I'm really only going to talk about some applications of weighted random walks on graphs, because there's lots of good questions that come about Kemeny's constant when you're thinking about applications. And so I'm mostly just going to talk about the applications. I've got good questions. I don't think I've got good answers yet, but that's okay. And then the other extension that we'll have is to think about non-backtracking random walks on graphs. So this is tied in with interesting results in mixing times. So non-backtracking random walks have also been studied with other metrics that kind of measure how easy it is to get around a graph with a random walk. And I I think there's a lot to be done here around the influence of graph structure on Kemeny's constant when you see how the non-backtracking thing changes stuff. So we'll talk about these two things. I'll probably end up speed running through the non-backtracking part because I'll just talk too much about the applications if I know myself. But we'll start there and we'll see how we go. Are there any other questions before we carry on? Okay, applications time. All right, so let me tell you what a weighted random walk on a graph is. I think this should be reasonably straightforward. You take a graph, and with each edge, you've got some weight associated with it. For those of you in the audience who are big fans of the quantum thing, maybe this is, I can't remember what it is with the quantum spin network. What is it, an entanglement or something like that you do to make the weight higher? We'll associate a weight with an edge. Anyway, we're just taking random walks, not quantum walks. And so the idea is that, right, still when I'm on vertex 2, I have 3 neighbors to choose from, but now my probabilities are just weighted by the actual weights of the edges. So I choose where to go to next, proportional to the weights of my edges. So I'm 4 times more likely to choose vertex 1 than vertex 4, and I'm twice as likely to choose vertex 1 than vertex 3. So essentially all you do is you take your weighted adjacency matrix and you just normalize the rows to get a probability transition matrix. That's all you do. So here, it would be 4, 2, and 1 as my second row of my adjacency matrix, and I just normalize by dividing by 7. So now I'm more likely to go to vertex 1 than vertex 3 or 4. Okay, all right. And so Kemeny's constant for this, just find the eigenvalues of your weighted transition matrix and go. All right, but let's talk about the kinds of applications. And so there's a list of them here, but I'm going to go into, I think, 3 of them in detail. And we're going to start with the robotic surveillance one because that's catchy and interesting sounding. And so this is a paper from 2015, the years fly, where they looked at robotic surveillance problem. And they used Kemeny's constant to solve this robotic surveillance problem. Now, what do I mean by a robotic surveillance problem? So the idea was they've got a persistent intruder in a fixed location in their environment, and their environment is divided into regions that can be surveilled by some autonomous agent in a single time step, right? So you've got a robot of some description that moves around the environment, okay? So the idea is that you represent the environment with a graph, where the vertices of your graph are the regions that your robot can occupy and surveil in one step. And then he moves from one vertex to another just by moving in the environment. Now, this might not be a physical environment. It might be some computer network, but I don't really know the details there, nor do I particularly care. And so the edges between the nodes, right, they're just, you've got edges between vertices if it's possible for that agent to move from one region to another in a single time step. So you've got some time step dictating things. And what they wanted to do was they wanted to find like some kind of instructions to give the robotic agent to search through the environment in as short a time as possible and to find this intruder, this fixed intruder somewhere. And so the idea was that Kemeny's constant for a random walk on a weighted graph would be a measure of the expected length of time to capture the intruder, right? Because it's the expected kind of length of time to reach kind of anywhere from a fixed starting state. And so we're talking about a random walk on a weighted graph here. What they wanted to do was find the weights that would minimize Kemeny's constant, right? How should you choose the weights of the edges, which is essentially the instructions to give to the robotic agent on which direction to choose at each juncture? How should the weights of the edges be chosen so as to minimize Kemeny's constant? That's the problem, okay? And what they proved, let me see if I get this right. So they determined an expression for Kemeny's constant as the trace of an appropriate matrix. It wasn't quite that fundamental matrix. It was a related kind of thing that worked for them in their context. And the reason that they had a slightly different formulation was that they wanted to essentially show that it was a convex optimization problem. So they show that the set of all matrices that achieve the minimum weighted Kemeny's constant would be a convex set. And so then what you've got is you just formulate the problem as a convex optimization problem and then solve it using semi-definite program, which I know next to nothing about, so don't ask me any questions about it. But essentially what they achieved in this paper was that if you hand them a graph, they can, plug it into their optimization problem and produce the weights that would give the minimum Kemeny's constant overall, so that Kemeny's constant is as small as possible. And so it would produce the weights on the edges that would achieve this. Okay, and it turned out that this, this was 2015 now, but at the time this was kind of outperforming the state of the art, which is super neat because it was quite a niche thing for people in control theory to think about something like Kemeny's constant, at least as far as I'm aware. Okay, that's application number one. Application number two, you can see by the date that this arrived on arXiv is that this was a very topical issue at the time, where in March 2020, COVID happened, and then everybody was trying to find interesting research problems that they could do while they were stuck in their houses. And so this was one that appeared on arXiv, which was Kemeny-based testing for COVID-19, where the idea was you have like a contact network. Here's your graph now for how individuals might spread a communicable disease to other people in their community. And now here you could have weights on your edges corresponding to how much time people spend in contact with each other. Okay, and so if you calculate Kemeny's constant for a random walk on this weighted graph, then that gives you a measure of, can I go backwards here? Yes, I can, okay. That gives you a measure of how easy it is for the disease to move around in the graph, right? The expected time it takes you to, it's a random walk. It's not how the disease is moving exactly, but it gives you a metric by which you can kind of compare. And the idea was that for every person in the graph, for every vertex, you compute Kemeny's constant for the random walk on that graph when you remove that vertex and then compare it with each other, right? And so you want to know which vertex, so which person causes the biggest increase in Kemeny's constant after its removal. Remember, big values of Kemeny's constant means it's hard to get around. And so if you have a big increase in Kemeny's constant, you've now made the disease it's harder to spread the disease now. So the idea was that these would be the people that you should vaccinate or quarantine or just kind of give a heads up that, listen, your contacts are spread. And so there was kind of two papers. There was this original one in 2020, and then this follow-up one that compared this introduced this idea. And then there was a group of us that kind of compared it with other centrality measures from network science, to see how well it performs. And the idea was that, right, if you kind of naively quarantined or vaccinated people based on the number of contacts that they had, that would correspond to their degree, right? And so you end up in graphs with a lot of clustering. You end up not really doing such a good job. Whereas when you use something like Kemeny's constant or other metrics like random walk betweenness and so on, the ones that give you the kind of highest centrality measure are the ones that bridge communities somehow. And so this kind of give you a much better way of controlling disease spread in the network because you're kind of separating it into communities much faster. Okay, that's application number two. I think I've got one more, which looked at a very similar idea, but with road networks. So here the idea was your graph represents a road network. And you have weights on your road. So like the nodes now are just intersections and you've got an edge between them if it's a road between those two intersections. The weight of the edge is like the capacity of the road, something along those lines. You take a random walk on this just based on the road network. And the idea was to find which roads in the network are most, play the biggest role in the connectivity of the road network. And so the idea again is if you have a weighted undirected graph, Kemeny's constant will indicate how well connected the road network is. So the higher the value, the less connected it is. The lower the value, the more well connected it is. And so if removing an edge from the graph causes Kemeny's constant to increase by a lot, then that's important to the connectivity of the graph. So if I go back to this picture here, The color scheme is not great, but the roads in blue are on the higher end. You can see that these correspond to bridges over the river, and for the most part, this is a big bridge over the railway. So these are the ones that if you remove them, cause an overall increase in Kemeny's constant. So those are the roads that are most important. Okay, and so I'll give you a kind of like the idea was, right, for every edge in the graph, calculate some centrality measure for that edge, which is the difference between Kemeny's constant for G without that edge and then the original Kemeny's constant for G. And so this gives you a centrality score for each road in the network. And there's a lot of content in this paper. I'm trying to decide based on time how much to do. The idea was, right, let's say this is your graph and you want to remove the edge from 2 to 4. If you were just working with the adjacency matrix or the weighted adjacency matrix, then all you have to do is zero out the right entries, right? And your perturbing matrix is just like a -1 and a -1 here. But once you start working with the transition matrix, not only do you have to like zero out a certain entry, but you also have to renormalize. And so your perturbing matrix here ends up being this mess. And so, I mean, there is a formula for it. I'm just going to fly through it and you can see it, and then we'll go from there. If you have the weighted adjacency matrix of the graph and you want to remove the edge between vertex I and J, then your perturbed adjacency matrix is like, you subtract off this rank 2 thing, right? And then your new transition matrix is going to be the old transition matrix plus this guy, U times V transpose, where this is what V transpose is. Don't worry about what this is. I'm just showing you that it can be done. I'm not expecting you to figure out how to do it by yourselves. And so the initial kind of centrality score that you get is that you can show that the centrality score is going to be the trace of this mess of a matrix. All right, so you can do it, right? You can calculate it. But most of this paper is dedicated to finding efficient ways to do this for every edge in the network. Now, I just want to mention that, like, when it comes to like solving problems that are related to applications, like once you get something like this, there's kind of 2 ways you can go, right? You can decide, I'm going to try and do this as efficiently as possible so that this is valuable in my application. The other thing you can do is you can try to mine it for insight, right? So you've got this expression, like under what circumstances is this large? Is it small? Is it positive? Is it negative? You know, this is kind of, there's 2 ways you can go. And this is mostly the way that was gone in this, was to find efficient ways to do this. And actually very quickly, they decided to discard this method of doing things. And instead, rather than like having to renormalize, when you delete an edge, rather than kind of distributing it amongst the other kind of choices you had, just add the lost weight to a loop at the vertex I and a loop at the vertex J. So now you're just kind of hanging around for longer instead of moving on. And it means a couple of things. It means that your centrality score is always non-negative, which means you don't have any brace edges, which is a really interesting paradox in road networks. And so, you know, they've kind of done away with that just for simplicity. It also meant that they could use the Cholesky decomposition, because their formula that they got had a positive semi-definite matrix in it. And now you can efficiently compute all the centrality scores and do it in order n cubed plus m, which I know that seems high, but if you're calculating Kemeny's constant at all, you're looking at n cubed in general. So this would probably be pretty good considering you're calculating Kemeny's constant n times. So this is not so bad. And so this is what the perturbation looks like, right? So instead of zeroing this out and redistributing, you kind of move it to the diagonal entry, and then your perturbing matrix is a rank 1 thing instead of rank 2. So it makes things a little bit nicer. Now that's application number 3. So what kinds of questions can we get from weighted random walks, like when we're inspired by these applications? Well, one thing is, like, say you're given a graph, what's the minimum value of Kemeny's constant over all weighted random walks on the graph? So I know that there's this theory that, you know, shows that you can find this using a semi-definite program. But if you just hand me a graph, like, what structures in there tell you about what the worst case or the best case are? Like, is there a way that we can determine that? Can we find, this is well studied, but still kind of hard. Can we find good expressions and bounds for the difference in Kemeny's constant after you remove an edge or after you remove a vertex? And then under what circumstances does the structure of a graph alone impose something about how Kemeny's constant changes? Here I've given one example that when you remove the edge, you decrease Kemeny's constant. So removing a road in your road network makes Kemeny's constant better, makes it easier to get around your road network. This is a brace edge here. But these last two questions, you may have seen them addressed before, but I'm specifically kind of talking about in the weighted case, where you've kind of got a lot more flexibility, and so therefore maybe you can't say as much. They're interesting questions and certainly very useful. So I'm going to just put those questions out there into the void, and after about a minute or two, I'm going to move on. Maria, have you a question? Oh, sorry, I saw you unmute. My bad. If there's any other questions, if not, we'll move along. Okay, so then I know this looks like it's the last section, but I think it's quite long. So let me see how much we do. So the other kind of slight generalization of simple random walks, we're going to go back to unweighted graphs. But we're going to start incorporating a little bit of memory into our situation. Okay, so this is tied, I said this was tied to kind of some known concepts within like non-backtracking random walks and mixing times. So there's this nice paper from 2007 that non-backtracking random walks mix faster. Now, what do they mean by mixing faster? It means kind of like your initial information about where you started is lost faster. So you get around in your graph much quicker. So mixing time here is measured by the size of the second largest eigenvalue of your transition matrix, or equivalently, the smallest non-zero eigenvalue of your normalized Laplacian. I think maybe I'm missing a modulus here, but this anyway, it's related to the spectral gap. And so it's kind of natural to now think about Kemeny's constant, because there's a paper by Hunter, gosh, I forget the year, 2011, 2009, where he gave an interpretation of Kemeny's constant as an expected time to mixing. Now, it's not quite the same thing as mixing time, though I know the name sounds very similar. But there's an interpretation of Kemeny's constant that, again, relates to how easily initial information is lost. And so, obviously, the next natural question is, do non-backtracking random walks mix faster when you measure mixing by Kemeny's constant than simple random walks? So if I don't backtrack, can I get smaller Kemeny's constant than if I do backtrack, if I'm just walking randomly? Now, I haven't said what non-backtracking means, so I need to give you an example of this. So the content of what comes next is this paper that I think happened almost entirely over the pandemic. I visited Utah in February 2020, and then a month later, I think I remember disinfecting my hands going onto the plane when I went to Utah. And then by the time I got back, it was kind of like, I should probably start wearing a mask. And so sorry, that was irrelevant information. But so this is a nice paper where we kind of just introduced the idea and tried a few small classes of examples. And so I'll try and talk about them here. But what's a non-backtracking random walk? Okay, so in a normal random walk, you occupy a vertex and you move to one of your neighbors, and you choose from your neighbors with equal probability. So with a non-backtracking random walk, you remember like one step in history, right? So if I've moved from vertex 2 to vertex 1, I just remember that I was at vertex 2, and I'm not allowed to go back there just in my next step, right? So when I'm in vertex 1 and I was previously in vertex 2, I now have 2 choices, and I choose those with equal probability. So now I have probability of 0.5 of going to either 4 or 3. So when I move, then I remember that I was at vertex 1, and then now I've only got one choice, so I move to vertex 3, and I have to remember I'm at vertex 4, and so on. Okay, now this is kind of hard to encode in an n by n matrix, right? And like without kind of going in, like you could go into the probability side and just have like second order Markov chains and so on. But it turns out if you only care about like one measure, like one step of history, then we can do this with simple random, like a simple Markov chain pretty well. And what you do is you just take all your edges and you turn them into like directed arcs that go both ways. And once I'm in the situation that, okay, I was at vertex 2 and now I'm at vertex 1, just think of that as being on the edge 2 to 1. Okay, and then when you're on the edge 2 to 1, then you only, like, your next choice is like, what edges can I go to next? Well, I've got these 3 choices. So if I wanted to see what a simple random walk on the graph looks like on the edge space, it would just be these, and I'd have 3 choices to choose from. And for the non-backtracking one, all I have to do is zero out this transition. Okay, and so now I've only got 2 choices. So you can model the whole thing with like normal Markov chains and normal transition matrices if you take random walks on the edge space instead. Okay, so some definitions for you here. So this is the transition matrix for the simple random walk on the edge space with backtracking, where now you've got a 2m by 2m matrix and it's defined entry-wise, where, I mean, as you'd expect, that you can get from the edge ij to the edge kl if the end of edge ij is equal to the start of edge kl. And then the probability is just 1 over the degree of j still. All right. And then for the non-backtracking one, you have an extra condition here where you can't have like L equal to I. And now you have 1 fewer choice. So it's 1 over the degree of j minus 1. Okay. All right. So these are our 2 transition matrices. And so I have some examples here. I don't know if it's worth dwelling on them, but here you can see that from the edge to 1, I did have 3 choices. And if I want to switch to a non-backtracking guy, I zero out all of those ones corresponding to the non-backtracking edges and then renormalize to get my non-backtracking transition matrix. Okay, and so my notation here, Kemeny's constant for PE, the simple random walk is just, I'm going to write it as KE of G. And then I'm going to have my non-backtracking Kemeny's constant, which is just Kemeny's constant for the non-backtracking transition matrix, right? And I'll mention that you can't define non-backtracking Kemeny's constant for graphs with pendant vertices, because then you just walk out and then you'd have nowhere to go because you can't backtrack, right? So you can't talk about those at all. You also can't talk about cycles, because once you start in a direction, because you can't backtrack, now your kind of state space is in 2 pieces, and Kemeny's constant is not defined as infinite because you can't mix through those states, right? So we're going to look at graphs with minimum degree 2 that are not cycles. That's all we can. It's just there and up. That's all we can do. Okay, and to compare the behavior of a simple random walk and a non-backtracking random walk, it makes more sense to just compare the non-backtracking Kemeny's constant with the edge space Kemeny's constant, not the vertex space one, because there's a different number of states, and so it just makes it higher. Calculating 2 numbers and looking at the numbers are kind of in different contexts, so it doesn't make sense. But the good news is, I'm going to motor on nice and fast now. The good news is that there's a nice, easy expression for Kemeny's constant for the edge space of a graph, if you know what the Kemeny's constant is for the vertex space. So it's just Kemeny's constant for G plus 2m minus n. And the proof uses a nice matrix factorization, which I won't go into, but it's essentially just like you factor your adjacency matrix into like by 2 incidence structures, like the start point incidence operator and the end point incidence operator. And then there's this nice theorem that says that, like, if you've got 2 kind of rectangular matrices and you're multiplying them and you switch the order of multiplication, the eigenvalues agree, but you just need to pad it out with a bunch of extra zeros, which is a super nice theorem. I really like the theorem. So you just have to do this for your transition matrices, which is a little bit of a pain, but you have some similarity transformations you can work with. And so here's what the proof looks like that I don't want to do. But the eigenvalues of your edge space transition matrix are just the eigenvalues of your vertex space transition matrix with an additional 2m minus n 0 eigenvalues, which means that when you plug them into that 1 over 1 minus lambda thing, you just get a bunch of extra ones. You get exactly 2m minus n of them. And so this is where you get that expression from. Okay. Let me quickly tell you what we did from there. So it turns out it's quite hard to deal with these matrices. And so we pulled a lot from some results on the non-backtracking adjacency matrix. So this was a paper by Mark and his master's student, who is also on this kind of subsequent paper with Kemeny's constant. And they had looked at a lot at regular graphs and the adjacency eigenvalues for regular graphs, both for non-backtracking adjacency matrices and the regular, and kind of comparing. And so we just looked at non-backtracking random walks on regular graphs to see if they mix faster and how much faster it can be. And it turns out there was kind of enough in there to keep us going. So for starters, we kind of, this is a standard thing to do in algebraic graph theory, right? If you're dealing with a spectral graph invariant and it's kind of uncomfortable in the matrix you're working with, well, if you look at regular graphs, then you can work with some of the other matrices that are a little bit nicer to work with. And so we express everything in terms of the adjacency spectrum. So here's your edge Kemeny's constant for a regular random walk. And then if you look at the non-backtracking one, you can express it in terms of the edge one. And so the proof of this just comes from finding the eigenvalues and plugging them into a formula and then getting those stellar undergrads to just do a bunch of computation and simplify. So you get this expression here, right? So now we can compare the non-backtracking Kemeny's constant with the edge Kemeny's constant. And so it turns out that as long as it's not one of these three, that the edge Kemeny's, so the simple random walk is always bigger than the non-backtracking one. So the non-backtracking one does mix faster for regular one. But how much faster does it mix? Well, you can show that it's between these two bounds. The ratio of these is at most one and is at least most one and at least 1 over 2 minus 1 minus 2 over d, where d is how regular it is. And so, well, how close can it be to these? Well, if you take okay, so there's a bunch of them where it actually exceeds it, but for complete graphs, in the limit, you approach 1. And then in the lower bound, if you look at this like 3 regular necklace graph, it's called, this is another Aldous-Phil conjecture guy that shows up quite a bit. So these ones, you can show that we approach the lower bound in the limit. For this class of graphs, right? Just again by calculating the non-backtracking one with the standard one and comparing. Okay, you can improve the upper bound a little if you fix it away from being like the complete graph. So if you fix the degree of regularity, then the biggest it can be is 1 minus 1 over d squared. And can you get equality here? Yeah, if you pick a deregular Ramanujan graph, the ratio will be close to the upper bound. Okay. From there, what we kind of had, I think maybe I'll skim over the next wee bit, because we had trouble from there, because if you want to compare like the non-backtracking Kemeny's constant for 2 different graphs, it's kind of weird if the 2 graphs have a different number of edges, because you've got a different number of states, because now the state space is your edges, the number of edges. So we fixed like we looked at the smallest possible class of examples where you've got n plus 1 edges in your graph, and then came up with these cycle barbell graphs, which look like they maximize both Kemeny's constant, the non-backtracking one and the edge space one. That these are kind of the worst case, that mix the worst, both if you're non-backtracking or if it's just on the edge space. So this is only within the class of graphs with n plus 1 edges. But the interesting thing was, I think that those are the expressions, don't look at them. That the cycle barbell that gives you the biggest simple Kemeny's constant on the edge space is where you make the 2 cycles as small as possible and the path between as long as possible. But for the non-backtracking one, the way to maximize was to take those 2 graphs, the 2 cycles, and make them as big as possible and put a really short path in between. And then in every case of the cycle barbells, the edge one was bigger than the non-backtracking one regardless. It's just the maximums were different. They were achieved at different ones, which is kind of weird. Okay, and so we've got a conjecture that based on our evidence, it looks like the non-backtracking one, as long as n is large enough, you'll always have the non-backtracking one being smaller. And so for the first few number of vertices in your graph, there's a few exceptions. But once you get large enough, there's 0. So we did exhaustive search, and this is what it looks like. And there's lots of questions you can ask in here, where if you've got a procedure that mixes faster, if you do non-backtracking, I'm particularly interested in how this relates to the robotic surveillance one, right? So if you had weighted non-backtracking random walks, you might be able to find your intruder a lot faster. But I'll leave those questions there. I didn't have any concluding comments, actually. I'll just say thank you very much, and I can return to the slide with the questions if you'd like to look at it for a little bit longer.
Thank you very much, Jane, for your talk. So to start, for which graphs do we know Kemeny's constant for which classes of graphs?
For which, what, sorry?
For which classes of graph do we know Kemeny's constant? So the cycles.
In terms of like a
fixed expression?
Ooh, let me go all the way back to the classes of, I don't know if there's like a, hang on, so we see. I mean, there's different like versions of an expression for, oh my goodness, there's a lot in here, isn't there? Here, there we go. Okay, so the ones that I can tell you about, because I was involved in them, the barbell type graphs, which are, hold on, I show it, these kinds of ones, right? If you kind of change the like parameters here where you have the size of the clique, the size of this clique, the length of the path, and then I think we also had an example where you had a bunch of different paths in between. You can just write out an expression involving like A, B, C, and D. It gives you a value for Kemeny's constant. It is a mess, and you kind of just flush away the lower order terms and you don't think about them. Let's see what else there is. For trees, there's an expression that looks like this, but is much nicer, which is based only on the distance between your vertices, because the number of spanning forests that separate two is now just the number of ways you can split the path between them. And so I don't know, it depends on what you mean by what do you have a closed form expression for, because they've all got, I mean, you can just find the eigenvalues and then calculate, but some of them work out nicer than others. So here's a bunch of examples where you can talk about them, but it's very subjective as to which ones you would call a closed form expression, I suppose.
Okay, thank you.
If that makes sense.